Good evening, everyone. Those of you who are on the call, so the way we set up this meeting, everyone is on mute, and the video is off as well. So if you have questions throughout the presentation, just use the chat feature and type your questions into the chat, and we'll address them throughout the presentation. So just a quick note on the ECS Detroit section for those of you who may not be familiar with us. So the section that we have, it's typical. So Tobias up at the top there, Chris, myself, and a couple others are the main members of the leadership committee of it. And our section itself, there's quite a bit of industry members. We do have members from the local universities, colleagues throughout the nation, the world. Our focus has really been more industry driven, but again, it's mostly the technical people and individuals from the companies that are joining this meeting. So a lot of the team members here, the participants, they're not necessarily ECS members, and that's something else that we do from our section. We open this up to, not just ECS team members, but colleagues, friends, others who might be interested. Obviously, we promote the ECS membership. It's a great way to connect with colleagues, to get access to all the ECS articles and everything as well. So if you have any questions, feel free to reach out to myself or Tobias or Chris. But with that, I'll turn it over to Tobias so we can introduce our speaker, Sergey.
Yeah, thank you, Eric. So we are proud to have a special speaker today, Dr. Kalnaus. He is a staff scientist at Oak Ridge National Lab, and he has spent years and years on solid state batteries and the mechanics of it. And he even, he didn't only publish lots of papers, he also helped write the book on solid state batteries and won awards about it. And he can say a lot more about it. So without further ado, I would hand it over to Dr. Sergiy Kalnaus. Take it away.
Thank you, Tobias. Thank you for introduction. And thanks everyone for attending this at late hour. Thank you for dedicating your time to be here. So Sergiy Kalnaus, I'm staff scientist at Oak Ridge, and I will give a brief overview of what are the roadblocks on getting to the working robust solid state batteries, and why do we need solid state batteries to begin with, and if there is a chance to design them so that they can withstand many electrochemical cycles without failure at different temperatures. And especially the role of mechanics in all this, since by training I'm a mechanical engineer. My background is actually in fatigue and fracture mechanics. But I got into batteries because they're so interesting. And there is a lot for a mechanical engineer to do in this area. So I'm gonna briefly say where I'm from. I would assume some people don't know what Oak Ridge National Lab is. It's cleverly hidden in the woods of East Tennessee, right here. And once upon a time, to be exact, back in 1943, as a part of Manhattan Project, they bought a piece of land here, which is quite remote from everything else, to start the X10 facility, which is the graphite reactor shown here for the Manhattan Project. So it's a part of other national labs. It's the largest one of them, I believe. And right now, this is what it looks like. It has two main campuses. One is the campus in Oak Ridge itself, that's where I am, and another is the campus, NTRC campus, which is in West Knoxville. It's about 15-minute drive from Oak Ridge. And this is where we have the battery manufacturing facility and additive manufacturing facility. We actually house a full industrial battery manufacturing line here, which can produce, I believe, up to 5 amp hour capacity pouch cells. So there is a pouch forming machine, there is a electrode punching machine, electrolyte filling machine, and all that. And we can pull the vacuum on those pouch cells and boil the tabs and test them there. I believe the total workforce is about 6,000 people. 2,000 of those are R&D scientists. So why are we thinking of changing something in terms of batteries and solid state? If you think about it, the design of batteries hasn't changed over many years, 60 years or even more. These are the pictures from the alkaline battery patent file by Marsal et al. In 1960. And this cylindrical battery form with the positive and negative electrodes separated by a separator, porous separator, remained the same over many years. There are obviously advances in rechargeable batteries, lithium-ion batteries, starting with Stan Whittingham and John Goodenough introducing lithium cobalt oxide into the system. So there's been a lot of research on increasing the capacity of the cathode material, coming up with different ways to manufacture the separator, but the overall principle remains the same. And this is what powers pretty much everything these days, from our laptops to electric vehicles. And just for fun, I have here what is called EMU, extravehicular mobility unit. This is what astronauts use when they do spacewalk. And this is the actual battery pack that powers it. And it powers pretty much everything from the oxygen supply to light to temperature control. So this is a very important life-saving device that they carry on themselves. But like I said, the basic operating unit of the battery remains the same over many years. You have positive and negative electrodes flooded with the liquid electrolyte, which has flammable solvents. It has a salt dissolved in the organic solvents, which are quite flammable. And the only thing that separates electrodes of opposite polarity is the separator, which is a porous polymer membrane. This is highly anisotropic system. You have particles that behave ceramics-like mixed with rubber-like binder materials and coated on top of the metallic current collectors. And the safety of this whole system relies pretty much entirely on the integrity of the separator, which is a critical component here. Once it fails, you have contact between the electrode, positive and negative, which releases a lot of energy. And since you have flammable liquids in the system, this can lead to consequences. Now, the thing is, there are not so many requirements on the mechanical integrity of the separator. If you look into the standards and literature, the biggest standard you can find is that it should withstand the tensile force of the winding machine when you're making a battery, and that's not much of a force, to be honest with you. So, fun fact: it being polymer, its strengths and its properties obviously greatly depends on temperature. And if you look at this graph, if you look at the operating temperature of batteries, just increasing it a little bit will decrease the Young's modulus by a factor of 2, well, depending on the applied strain rate. This is intention for the Celgard separator. And another fun fact, it takes only 35% of biaxial strain to break it. This was part of the Department of Transportation project sponsored here to find out how the pouch batteries fail due to the penetration of the trailer hitch through the battery pack. So it's only 35% strain. And then you have a failure, and then bad things happen, something like this. These are all very familiar pictures that everyone probably seen online, except maybe, let me see if I can get the pointer going. except maybe this beautiful firework. And believe it or not, this is actually the battery from that EMU unit that the astronauts carry on themselves. So this is what happens when you get the short circuit and thermal runaway in that system. So it's only natural that instead of dissolving salts and having electrolytes with limited transport number and highly flammable properties, it would be nice to switch to something else, more safe, with the transport number close to unity as possible, and having transport over the crystallographic lattice rather than by dissolving the salt in the liquids. And so these are the advantages of solid-state batteries, which are, some of them are quite obvious. As I mentioned, there is no electrolyte to burn, there is no gassing, there is no need in sophisticated fire protection systems as a result of that. You can get to the higher voltages, especially if you use metallic lithium as your anode, which creates the highest possible potential window. And the last three are very interesting to me, especially because since these are solid state, you can reimagine how they packaged, you can reimagine how they made. In the extreme visionary cases, you can even imagine them being 3D printed into different shapes because they're so flexible in shape and form factor. You can introduce them as the wearable technologies. And finally, because solid electrolytes, if they're designed properly, are quite stiff, you can integrate them into the structural components, potentially. So these are all advantages. Looks good on paper. It's a great idea, but we are still kind of far from realizing it. And last year, in 2020, I believe it was back in May, Oak Ridge held a big workshop on what should we do to move it a little bit closer, what's missing in this picture, and what should we do to move it a little bit closer to the reality. We had about more than 30 participants from other labs, industry, and academia. Everyone shared 2 or 3 slides with their interest and progress and ideas. And all this was summarized in a technical report, which is freely available from OSTI website and as a letter in ECS Energy Letters. Now, out of all this progress, so this graph here shows how exponentially the interest in solid state grows just based on the number of publications every year. So this statistic, 1 year old. And if you analyze all those publications, you can put the spider chart here indicating which area is most developed and least developed. And we have a good progress in terms of material synthesis. We have a lot of solid electrolytes being developed. We have less knowledge on how to put those solid electrolytes into a battery, integrate with the cathodes into something working. And there is not much knowledge on the mechanics, whether it's important or not, mechanical properties of the components, and how to make all those battery components to play nice with each other and create robust interfaces. So this mechanics part is probably what I will be focusing mostly in this presentation. Now, the key for the whole solid-state battery deal is the electrolyte, because it should work with the lithium anode. And throughout the talk, the anode here is metallic lithium, because it only makes sense to move to solid state if you have metallic lithium as the electrolyte, because that's when you push your energy density to the maximum. So it should interface lithium anode, it should interface cathode particles, presumably the same cathode particles that we know are working now in the conventional batteries. And at both interfaces, there is a chance for fracture. There are mechanisms for stress relaxation, about which I will talk. There is obviously, since we're talking about lithium, which is highly ductile material, there is obviously influence of plasticity and creep, but it doesn't always operate. Again, I will talk about it in a few slides. And when it comes to the interface with the anode, simply because repeated insertion and removal of lithium-ion creates strains, we're well aware of that, especially in the layered transition metal oxide materials. You have strains along the z-axis, so your electrolyte should maintain contact with those particles throughout the cycle. That's the idea. And there's a good variety of electrolytes to choose from. If you recall that spider chart, the advancement in material synthesis has been pretty much tremendous. Some of them, like sulfide materials, they approach the ionic conductivity of the liquid electrolytes. However, there are two major areas where they fail. And again, in here, I'm not talking about polymer electrolytes. I'm talking about ionic conductors in form of ceramics and glass. They fail in contact with cathode because of the repeated cycling. You have kind of a fatigue. Some of those cracks appear immediately. Some of them propagate with time. You have cracks at the interface between the active material particles and the electrolyte, and you have the cracks in the electrolyte itself. So this example of the LPS with NMC, I believe this was 62 from the Yamamoto group in Osaka, and they fail in contact with lithium, what we collectively here being called dendrites. Trying to stay away from this term because these are really not always fractal structures typical for dendritic growth, and we carefully call them lithium filaments. But in any case, with contact with lithium, seemingly very ductile material can lead to the fracture of the solid electrolyte and propagation of those lithium filaments which short the cell. So the idea of moving away from those separators that are not strong kind of gets diminished if you have electrolyte that fails in a brittle manner. So how do we deal with that right now in the lab? How do we deal with that separation along the interface is by applying tremendous pressures to the experimental cells in the lab, tens of megapascals. And if you compare that to, a few kilopascals that you get in a normal battery pack inside the car, these are tremendous pressures. Again, as the example here is the beautiful cycling of the solid state cell with LPS electrolyte, sulfide electrolyte, and NMC cathode. But look at the pressure applied here. This is a small experimental cell, of course, so they can afford that. And it comes again from the same group in Osaka University. But if you recalculate this 75 megapascals over, I don't know, 20 by 30 centimeters power cell, that's going to be 20 tons or something like that. So it's really non-realistic pressure to make a battery work. And going over all that, you can almost compile a list of wish list of what you would like from your ideal solid electrolyte. And the pieces in bold here is what I'm in particularly interested in. And I think these parameters here play a very important role in the robustness of the electrolyte. So it needs to be ductile enough so that it can deform together with the cathode particles without losing the contact. Yet it needs to be stiff enough and have high fracture toughness to prevent lithium from penetration. It needs to have high hardness as well. So some of these things here on this list are almost contradictory to each other, because most of the material, if they have high hardness, they also brittle. But as I will show, there are some ways to introduce some ductility into these materials. So let's look at the battery cell from the mechanics perspective. This is what mechanical engineer would see. Can you tell me if it's right or wrong? You have defects. First, let's start with the interface with metallic lithium. It doesn't have to be lithium. We hear a lot about sodium batteries as well, but it's interface with the metal, and you have plating into this void coming from the other side of the electrode of the cell stack, which creates the pressure. And this is where you start this war, this kind of competition on what to do with this stress buildup. So you cannot build it up infinitely. You cannot build up elastic strain until very high values, right? It needs to be released somehow. It can be reduced by inelastic flow in lithium itself by triggering some kind of dislocation motion in lithium metal, or creep, depending on the time scale. It can be relieved by inelastic flow in the electrolyte itself. And the third mechanism, which unfortunately we encounter in majority of the cases, is fracture that will reduce the stress buildup. So our goal here is somehow trigger these two mechanisms in either lithium or electrolyte to avoid the third way to reduce the stress. So let's start with ways, what happens in metallic lithium at the appropriate lengths and time scales. So lithium metal, I believe it's body center cubic. It has very high homologous temperature. At room temperature, it's 0.6. So that means it creeps even at room temperature. It's very, very ductile in its bulk form. These are the tensile tests that were done on the metallic lithium ribbon. With digital image correlation, you can see a lot of necking. It can take a lot of strain, and it flows plastically very beautifully. And in bulk form, its yield stress is from 0.5 megapascal to 1 megapascal. Basically, anyone who builds a half coin cell with lithium metal knows that it pretty much spreads almost as butter in its bulk form. As you go down in length scale, however, things are slightly different, and the general rule of smaller is stronger applies here as well, with some exceptions. So this is a plot which shows yield stress, or using Tabor equation, 1/3 of the hardness, to compare results from nanopilar compression and results from nano-indentation. So this is all compiled from different publication, and nicely shows how the strength of lithium increases as you go down in length scale. However, there is this curve here obtained at relatively slow strain rate by nano-indentation by Eric Herbert. And you can see that even at the small length scale, you have lower strengths of lithium compared to the high strain rate experiments. So this has been checked over many different samples, and you can see it here as well. As the length scale of your defect increases, your strength of lithium, hardness, or ability of it to support some pressure goes up as well, and then it goes down. So this is a very interesting mechanism, because what happens is if your defect is very, very small, lithium can relieve stress by diffusion. Since the distances are very small, it has just enough space to reduce the stress buildup simply by diffusion. If your length scale is large enough, it can start relieving the stress by dislocation motion. But if there is a defect of just the right size in between those regimes, it will build up stress to the very high levels. So this is what can be called as a danger zone. So this is quite a peculiar behavior of lithium. Obviously, this depends on the strain rate, or you can say, on the applied current density, and it depends on the length scale as well. So what can be very ductile and very soft in bulk becomes extremely strong as you go to the smaller length scale, which are length scales that we encounter with lithium filaments that propagate. Okay, so if lithium cannot reduce the stress, if you get the defect size just right enough to build it up, this job falls to the electrolyte. And here we encounter a huge problem because there are not so many mechanisms in ceramics to reduce the stress. The ceramic electrolyte, they hardly activate any sleep systems, at least not at room temperature, to reduce the stress, and they would rather fracture than make dislocations. It's very, very hard to introduce dislocations in ceramics. So fracture for them is energetically more preferable mechanism. And this table here, okay, let me go back. How do we measure resistance to fracture in mechanics world? By measuring fracture toughness. This is this parameter here called K1C, which indicates critical stress intensity factor required to propagate existing crack. So you have very sharp crack inside the material. You keep loading material until that crack propagates to failure, and that's your fracture toughness. In simple words, it's a resistance of material to propagate an existing crack. And if you look at all these values compiled for different garnets and perovskites and massicons, they're generally at around 1 megapascal square root per meter, which is very, very low. The same fracture toughness from the metallic materials would be 20 megapascal square root per meter. So this orders of magnitude difference, and it's not a big surprise. Ceramics are brittle. This table compiles values of fracture toughness obtained by different methods, and we need to be really, really careful how we compare them, because fracture toughness obtained from single edge notch bending represents the strength of many grains. It's really a bulk measure, and fracture toughness obtained from the non-indentation is a totally different measure. And
Dr. Kalnaus, we have a question. If we can, because it's related.
We have 2 questions. Yeah, sure.
Sorry, because it's related to slide 17, I think. There's a question from Matt Petraquila. I'm sorry. Is the length scale versus strain rate of interest primarily in electrode thickness, or would this be considered a potential limitation of pouch cell form factor size in the length times width dimension for material creep?
Right. So the length scale shown here is of interest in terms of the surface defects that you encounter on the surface of solid electrolytes. So this tells you that the processing of your solid electrolyte needs to be pretty much impeccable, so you don't have any voids or grain junctions where that create defect of just the right size, so that lithium will create high pressure in it. It does not affect the form factor of the battery itself. It's density and size of the interfacial defects in the electrolyte. If it makes sense.
Yeah, we can ask Matt if you want to say something.
Yeah, that makes sense. I think just the length scale of what we're talking about is a lot smaller than what I had.
Right. Yeah.
Perfect. Thank you. So feel free to type in questions there, and then we will address as we go. Thank you.
Thank you. So yeah, these properties need to be investigated at the relevant length scales, so that comparison of apples to apples can be made really. And the relevant length scale is again the length scale of those lithium filaments that we see, or the defects in the materials. So that's from fraction of micrometer to tens of micrometers. probably for relevant solid electrolytes. And non-indentation is a great tool for this. This is just a snapshot of the non-indenter that I use inside the SEM. Very convenient system. You can kind of see what you're doing right away with the electrons. And to probe the fracture toughness at the nanoscale, we typically use the cube corner non-indenter tip, which displaces 3 times more material compared to the Berkovich non-indenter tip. So you really create very high stress inside the material to reduce the threshold load for fracture. And here is the illustration of the problem that we're dealing with. These are some from our experiments, some from the literature. What happens in the majority of the solid electrolytes, crystalline solid electrolytes that are out there, these are the residual hardness impressions done by the cube corner non-indenter, and you can clearly see these cracks propagating from the non-indentation. And if you do this tedious, almost sadistic experiments of doing this many times and measuring the crack lengths, you can numerically calculate the fracture toughness and get exactly those values that are shown in the table. Most of them are 1 megapascal square root of meter or less. So this sounds like we're almost doomed, because all of the materials fracture, all of them will let lithium dendrites go through, deposit into those fracture surfaces. But there are actually some ways, there is a glimpse of hope. There are some ways to impart some ductility into ceramics. Oh yeah, I need to mention that these properties, fracture toughness and elastic properties, very often depend on the composition and are connected with the ionic conductivity of the materials, as shown on these 2 examples, one for the LLZO garnet and one for the massicum electrolyte. The nature of this dependence is still unknown, but it can fluctuate quite a bit depending on the composition of the material. So are things really that bad, and what can we do to make it a little bit more robust? So one scenario that is kind of picking up attention in literature, and I think in many cases it's the way to go, is to introduce dislocations into ceramics during the manufacturing. So generating dislocations in ceramics is hard. It's very hard. That's why they fracture so easily. But moving the existing dislocations is much easier. So the question is, why not implant the dislocations? And this procedure is known as dislocation toughening. You can implant dislocations into ceramics just by using different processing methods. And what is shown here, I believe this dislocation toughened titanium was produced by flash sintering procedure. Another procedure that can plastically deform ceramics and introduce dislocation is aerosol deposition, where you accelerate particles to very high velocity, and due to impact, you generate a lot of deformation and dislocations. But the results are quite clear. If you see very clearly, you can see the cracking here, and after dislocation toughening, the same beakers indentation produce no cracks. So that could be one of the potential routes to battle that brittleness in ionic conductors, in crystalline ionic conductors. And another way is to use ductile electrolytes and step away from the ionic crystals and look into the glassy electrolytes. So amorphous or glassy materials are very weird because in addition to just fracturing, they deform without conserving the volume. They can densify. They have just enough free volume to absorb plastic deformation by densification. So they have 3 mechanisms to reduce stress. Ceramics pretty much has only one, fracture. In case of glasses, you have 3 ways to reduce the stress buildup. And one is it can densify, the material can densify. It can flow in shear, very surprisingly. Actually, glasses can float, can produce somewhat plastic deformations similar to metals. And obviously, the third mechanism is fracture. And again, our goal is to find the material that can densify or flow in shear, but should not be fractured. And it seems that LiPoN, I have to be patriotic about LiPoN since I'm from Oak Ridge. LiPoN is one of those materials. So this is a simple comparison of a commercial borosilicate glass, which has glass formers inside, so it has pretty rigid structure. And LiPoN indented by the cube corner, and this actually indented to 50 millinewtons, and this is to twice the load. And you can see that LiPoN deforms, shows very substantial pileups. It deforms in shear without any evidence of cracking. So this is very high load indentation. The non-indenter went down to more than 2 micrometers down into material without producing any cracks. So this unusual behavior has something to do with the structure of LiPoN. That's why it behaves so abnormally. It doesn't have a rigid structure. The phosphate tetrahedra is relatively free to move around in this almost a soup of alkali ions here, of lithium ions. And it's relatively free to slide with respect to each other and deform bond angles. And the amount of nitrogen that connects those tetrahedra is relatively small. So it allows it to deform without producing any cracks. And this is kind of a summary of where LiPoN stands compared to the other electrolytes and commercial inorganic glasses, comparing the fracture toughness and its stiffness, elastic modulus, from different, is taken from different references and from our own work. So using the MD simulations, you can kind of look at different compositions and see how the deformation partitions into the densification and shear. This is, of course, simplified case. This is not truly non-indentation. You have a slab of material and you have a wedge going inside, but judging by the material pile up at the edges, you can tell about shear deformation, and judging by the densification, average distance between the tetrahedra under the indenter, you can see how much densification is occurring. And all the simulations are unfortunately done without nitrogen, simply because the force field for composition with nitrogen is not known. But we don't believe nitrogen would change this behavior too much. But what is clear here is that the material with the highest concentration of lithium or alkali ions in the system exhibits most of the shear deformation. And this is exactly, so we have 3 lithiums per 1 phosphorus. So this is exactly what we have in LiPoN. And the take-home message is that high alkali content promotes the shear in this material. And again, no fracture has been observed, at least under these loads and these strain rates. Now, the weirdness doesn't stop there with LiPoN. So this is a part of the load depth curve from the non-indentation, and this is the part of the unloading segment. And typically in the routine practice, what we do here after unloading, we hold it at the 1/10 of the peak load. So if the peak load was 50 millinewtons, you unload and hold it at 5 millinewtons, just to estimate if there is any thermal drift in your experiment. Now, being very careful, we measure thermal drift before the experiment as well on fused silica, and it should be less than 0.1 nanometer per second. If you look at this displacement here, it's much larger than that. So what this tells us is that LiPoN somehow can restore deformation with time. It has this creep-like time-dependent behavior when you unload it, and it restores the deformation. Most likely it's the densification that gets restored, because restoration of that shear pileup is simple and feasible. So it can densify and then restore that free volume a little bit. Now, this is not new for many glasses. Many glasses can do that, but you will need to input some thermal energy into material to allow it to restore this deformation. And LIPON, this happens at room temperature, which is absolutely bizarre, and which inspired us to do this weird test where you apply the sawtooth signal to the nano-indenter. You indent it to the peak load, then you load it to 1/2, and then higher and load to 1/2, and so on and so on. At each segment, you hold it for some time and you observe the deformation, and this is again the bizarre behavior. You see this almost hysteresis loop where again at each unload and cycle, LIPON restores its deformation. So potentially what it tells us is that it could work very, very nicely as a barrier buffer material between the cathode particles because it almost can breathe with the particles back and forth. So these cycles, these are what, 10 cycles or so? So this needs to be repeated obviously for many, many cycles. Maybe there is a fatigue factor here, maybe it will fail at the end. But at least as of now, this looks very, very promising material and somewhat bizarre. So other possible solutions that people looked into are composite electrolytes, where you mix polymer matrix with the ceramics filler, and your polymer matrix, just like in any other composite engineering, you impart strengths by ceramic filler, and the polymer matrix is supposed to do ductility and play a role in the ion transport. And however, if you do that with the very dry polymer, addition of the particles of the single ion conductor actually does more harm than good. So this is a simple numerical experiment where you have purely polymer electrolyte domain, then polymer electrolyte and the single ion conductor, in this case, LATP membrane placed right in the middle, and the polymer electrolyte and the composite in the middle. And just to see what placement of single ion conductor would do to overall gradients of the lithium cation concentration in the system. The hope is that it will reduce the gradients and increase the transport number. But if you do like I said, the simple numerical experiment, you can see that the effect is actually opposite. If you place composite electrolyte in the middle here, because you still need to observe the electroneutrality in the whole system, right? You develop much higher concentration gradients and obviously much higher polarization at the end. Unless you place the barrier in the middle, which is not penetrable for anions in the polymer, in that case, you split this domain into two subdomains, and in each subdomain, you have to observe electroneutrality, and the overall concentration gradient obviously diminishes. But using composite electrolytes with the dry polymer doesn't seem to be that feasible. And this has been confirmed experimentally as well. You can compare the simulation results with the experiments. So to overcome that, people use composite with plasticizers. They can be quite robust, and they promote ionic transport through the polymer phase. And in addition to that, they improve the transport number by tethering the anion from the salt around the single single ion conductor particles. So I think I'm going to stop here. These are just the acknowledgements of people who sponsored this work and my colleagues, and we can start the questions. Thank you.
Oh, thank you so much. Very, very interesting talk. I've learned quite a bit, and yeah, I'm a big proponent of LIPON, so that was very nice to hear that that there are some interesting benefits to that material. So I don't see any more questions in the chat right now. However, we have this opportunity today. We have a Zoom meeting rather than a webinar. So you can also raise your hand and we can unmute you and you can say your question. But you have to make yourself heard.
So
Yeah.
Before we move to questions, I have to make one disclaimer about Lipon. As fantastic as it sounds, as of now, there is only one way of making it by sputtering, right? By magnetron sputtering. So we know it works. We know it works for thousands of cycles, but only in a thin film battery form. It has been licensed to many companies, and if there is a way to make this glassy electrolyte in the bulk form, I think that would be a game changer for solid state.
Yeah, well, I've seen work at the University of Michigan that we had supported with Professor Lane, where we made it from polymer precursors in different stoichiometries too, and I've heard of a couple different ALD methods that might work.
Right.
I think there's some progress in that area.
Right. Well, you almost envision some methods of making float glass, like, I'm pretty sure Corning is looking into that. And there is a professor at Iowa State, Steve Martin, who's trying to make these materials in more bulk form. So,
besides
working with this group on that.
Yeah, I mean, besides Lipon being interesting as an interface layer in cathode and anode, what would you say for all the other electrolytes? What direction would you choose if you had to design a solid-state battery?
Sulfides are the most promising. They also have high ductility, like LPS glass. They have problem in terms of temperature requirements for it to work. It has to be at slightly elevated temperature and sensitivity to the atmosphere. So everything has to be handled in the inert atmosphere. So that generates its own requirements.
I see.
Well, I have a general question. This is Eric again. So Sergey, do you see maybe near term from the industry side decoupling, the solid state electrolyte and the lithium metal anode as well? I know you touched on it briefly. Clearly you don't get the benefits of the energy density, but do you see some of these solid state electrolytes working with a more traditional anode like a graphite or a silicon blend type?
Right. Yeah, most likely you would, unless you change your perspective of how this battery needs to be made. You see, the problem is we have synthesized a lot of different electrolytes. You can bulk them in powder, you can buy them in bulk powder form or in tape. There's a lot of electrolytes that we can use, but there is no good recipe on how to integrate all that into the cell. And if you switch your anode into the composite anode, you would have the same problems. Let's say with silicon, you would have the same problems that you have on the positive electrode side. How do you absorb all those humongous strains from silicon into that electrolyte? So it would need to be even more ductile. Unless again you want to put an elephant on your cell when you cycle it. So
and that's probably a good transition to Marcus' question. Could you comment on the need for pressure in the solid state cells? I think you had a brief slide or a brief discussion on it at the beginning, but if you could go back to that.
Yeah, that's just a simple brute force of keep all the interfaces together. Because these cracks appear, you have dimensional changes in the particles, active particles of your material. And imagine the same thing happening on the negative electrode side if you use silicon, which can deform to hundreds of % of strain. So these cracks will appear, and this is where the contact will be lost. So you don't have the transfer of your ionic current into the electronic current at this interface anymore. So to keep all these interfaces together, people apply very large pressure to the battery stack, just to keep everything close to each other. And just simply by jumping, this is one of the examples, jumping from 50 megapascals to 75 megapascals, you can increase the performance of the cell. But then again, 75 megapascals is okay if your footprint is, tiny little experimental cell. If you apply that much pressure over large pouch cell, let's say from Ford Focus EV, for instance, that will require a lot of force, very impractical.
Mark, I unmuted you in case you want to add anything.
Yeah, no, that, I'm quite concerned about these pressures, and if you have, if you're scaling up and trying to make large pieces, if you have any kind of flaw, and are you just going to crack your solid electrolyte? That's one of the things that I'm concerned about. But yeah, those are huge pressures.
Yeah.
Mm-hmm.
It's a brute form, brute force method of keeping your interfaces together.
Yeah, I find it hard to believe that it's a practical solution.
No, not at all, not at all.
Yeah.
We do like to keep cells under pressure in the battery pack, obviously, but it's obviously orders of magnitude less than that. This is very much impractical.
And we have a question from Susie Juan. I'm going to also unmute you in case you want to say something to it. The question is how to make thin solid electrolyte film that has similar thickness as a polypropylene separator, a cell guard or so. When all solid state batteries can be commercialized. That's it. Oh, that's the second question. When can the all solid state batteries be commercialized?
So the first part of the question is easy. You just increase the deposition time. These are made by RF magnetron sputtering. So you pretty much deposit it atomic layer by atomic layer. So to get to typical 25 micrometers thickness, you would have to deposit for a few weeks. If you have luxury of doing that, so that's easy. The second part of the question, when we're going to see commercial solid state batteries, is much harder to predict. At least 5 years, not in thin film format. Yeah.
Great, thank you. And then let me see. Chris, our team.
Yunji has a question.
Oh, am I not seeing something?
There is a raised hand by Yunji.
Oh, you. I'm sorry. Let's do Chris's question real quick. Is it practical to have separated / stratified layers of solid state electrolyte in a cell with different mechanical properties, such as hardness and elasticity?
That is a very, very good point. I would answer yes. There might be some engineering strategies. And again, the forms of the electrodes, we don't have to be making the same electrodes when you mix particles with binders and with the electrolyte, and then cast all that on the current collector. There are other ways of making electrodes. Free state casting is one of them, for instance. It's a process very known in ceramics industry, but it's picking up in battery manufacturing as well. Marka would know a lot about it. So, yeah, designing electrolytes with different properties of the portion of electrolyte that interfaces cathode and lithium is a great idea. And using LiPo as such a barrier has been tried and proven to be working. Yeah. It increases the cost of the cell, obviously.
Interesting. I hope that answers the question. We can, yeah.
Yeah, I'm good. Thanks.
Yeah, okay. Unji.
Yeah, hi, Sergey, thank you very much for the wonderful talk. So I want to circle back to the pressure issue, the screen that you're actually showing here.
Yeah.
So yeah, you nicely described the the relationship between the pressure and the crack formation. But looking at this data, it looks like it's not about the cycle stability. It's initial performance is also affected by the pressure a lot. So have you looked at, is it because of like this kind of high pressure is changing the electrochemistry fundamentally, or it is just kind of a kinetic issue?
Well, yeah, that's a very valid question. When you have 75 megapascals pushing on it, you might be changing the potential, the chemical potential of lithium at this high pressure. That's a very good point.
Okay, thank you.
Typically, you don't do that. We never go to such high pressures to change the potential of lithium, but at 75 megapascals, there is a chance of that.
Is there kind of actual work that's going on about the relationship between the pressure and electrochemistry? This is something that I have never, yeah. Okay.
Well, it's mostly theoretical. There are ways to describe it, of course. Yeah.
Thank you.
Thank you. That's a very, very good point.
We have a question from Evan. I also unmuted you. I read the question. Will the deformable nature of the electrolyte be able to reduce overall reversible and irreversible cell expansion over life of the cell?
Yes, if it can absorb the strains coming from the electrodes, yes.
Evan, does that answer your question?
Yeah, I didn't know if you had any kind of magnitudes. I've heard like, 15, 20, 25% expansion over life. So, at what point can it get down to more, real world numbers like we see today?
Right. That would obviously depend on the cathode material that you use and anode material, the amount of the strain that goes into that electrolyte must accommodate. The real question if this can be done repeatedly, and that's something we don't know even in the case of LiPo. I mean, again, we know it works, but it's in a very simple thin film format. But if it can deform and restore the strain over many, many cycles, that still remains an open question. There is a chance that it can densify only to a certain point, and then it will start cracking.
Okay. Thank you.
All right.
Lots of work for us to do. Yeah.
Good. So I think I don't see any more raised hands or questions. Last chance. Then I would like to thank our speaker for this very interesting talk. I'm going to use the clap function here to show my appreciation. And so the Detroit Electrochemical Society section is, we're very, very happy to have you speak here, and it was registration was very popular, and thank you so much, and have a good evening, everyone. Or Chris, did you want to, or Eric, did you want to add anything?
No, I think it was well said. I think it was good. I'm good.
I can see there are 8 messages in chat, but somehow I cannot get to it.
Thanks for the talk. I see.
Okay, so these are not questions. Okay.
No, I think we're through with the questions. So wonderful.
Okay. Thank you.
Yeah, thank you again, Sergey, and thanks to everyone who took the time to join today. We look forward to you all again joining in the future.
Great. Thank you very much.
Take care.
Thank you, everyone.
Good night. Bye.
Bye.